Welcome to another vodcast on Newton's Laws problem solving. We're going to take a closer look today at another general category of problems that I call multi-body problems, where more than one body is moving and they're connected in some fashion. Right? They're moving in some synchronized way so that you might call the collection of those moving bodies a system. You see on the screen several examples here. Okay, the one in the middle is actually referred to as an Atwood's machine. Okay. And sometimes I call the one on the left like a modified Atwood machine because it's basically moving in the same way, except one's moving horizontally and one's moving vertically. And then on the right we have another multi-body problem. So you're going to work some of these examples on your own in class, but I just wanted to work one example today and show you some of the other issues that come up as you work through a multi-body problem, and also that there's another option available to you when it comes to solving multi-body problems, one that's elegant and saves you a little bit of work. So let's dive right in. I'm going to focus on a specific example. Let's look at the next screen. We're going to look at this problem here. Okay, so we have a mass on a table, and we're going to assume for now that the friction is 0. Okay, so no coefficient of friction. We're not working friction currently in this unit. And hopefully you'll see that the block, right, the whole system is going to move to the right. So obviously this block's going to move up, right? This block's going to move to the right, and this block's going to move down. So you're going to start this problem like you do any problem, and that is you are going to draw free body diagrams for each of the blocks. So I'm going to pause and come back with those drawn in for you. All right, you see on the screen the three free body diagrams. And notice that for each free body diagram, I did pay attention to the relative magnitude of the arrows that I drew. You know that each of these blocks is accelerating, so there should be we should see an unbalanced force situation, right? We should see unbalanced in the direction of acceleration. So look at M1 here, right? This one, okay, is unbalanced up because it's accelerating up. This one here is unbalanced to the right because it's moving to the right. And M3 is unbalanced down because it's moving. It's not, see, I say moving, but I mean accelerating down, right? Remember, motion by itself doesn't mean unbalanced force because Newton's first law, right, dynamic equilibrium, objects in motion stay in motion all by themselves. They need to be accelerating to be unbalanced. So what we need to do now is just what we've always done, which is to translate these free body diagrams into equations. But notice we have 3 objects, so there's 3 equations. So that's going to take a little bit of writing. I'm going to go to the next screen and do that. But before I do so, I want to clarify something that we do with these kind of problems. When you have blocks that are moving or objects that are moving sort of in some kind of harmony, right? They're moving together in some sort of coordination, like the movement of one is directly coordinated to that of the other. Even though they're moving in different directions, you can put them in the same dimension. So what I mean by that is this. M1's moving in the positive y direction, right? This is a positive y here, okay? And then this is positive x, and then this is negative y, right? So on our piece of paper, it's like 3 different directions. But what I'm saying is that for the purposes of writing F equals ma, you can call all of this one direction, right? You can call all of that one direction. We can coordinate those accelerations because the displacement of this is directly correlated to this displacement of m2. And so on. So we can correlate all those accelerations and effectively call that one direction. Okay, you're going to see what I mean by that when I write my equations on the next screen. Notice, by the way, that M2 does have vertical forces acting on it, right? There's the weight, its weight balanced out by the normal force from the table. That's not really going to factor into our solving in this particular example, but in the next unit, when you have friction, you're going to need to use those vertical forces to determine the force of friction. But for now, the vertical forces aren't really going to enter in. And by the vertical forces, I only mean, these vertical forces right here, okay, on M2. So let's look at the equations on the next page. All right, so I want to write F equals ma for 3 different ones. So notice that my y column is real narrow. I'm not really going to use it. I just put it there really for effect. In fact, I'm probably going to move things over just a little bit more so I can maximize my space. So you see what I aim to do, right? F equals ma for each of the 3 masses. I'm going to pause and do that now. And this is, again, just reading my free body diagram right into the left side of the F equals ma equation. All right, that's what the equations look like. Notice, by the way, that I have 2 different tensions, right? I want you to notice that as well. Let me go back to the previous screen. Notice I had 2 different ropes. And I didn't assume that they had the same tension. In fact, if you look at M2, you know that you know that these can't be the same tension, right? Otherwise, M2 wouldn't accelerate to the right. Okay, T2, tension to the right, has to exceed the tension pulling it backward. All right, so what you have here is basically you have three unknowns, right? You have the acceleration, that's an unknown, which is the same in each case, okay? And then you have the two tensions. So you have three equations, you have three unknowns. Good luck, how about it? Woohoo! Three equations solving simultaneously, right? No fun. But totally possible to do, okay? I also want you to look at how the signs correlate, right? In other words, in this situation for M1, T1 was positive because that's the direction of acceleration, right? Whereas in equation 3, the tension was negative, okay? Again, I'm making, because on M3, T2 is pulling up, which is opposite the direction of acceleration for M3. So notice how I made all my signs agree, okay? All right, what I want to show you here, okay, this is sort of the object of this lesson, is that in this particular example, you have another choice, okay? You can look at this set of three masses as a system, like basically treating it as one mass rather than three separate masses, and that's going to allow you to solve things much more simply than having to solve these three equations. You can do it, right? It's just tedious algebra. So let me show you what I call the system approach, okay? So we're going to go back to the drawing, and I'm going to sketch it a little bit differently. In the system approach, we do the following, okay? We consider, and then I'm going to draw this dotted line around what I'm treating as my system, okay? Which is, it's not perfect, but I'm going to treat those three, since they move together anyway, we're going to just treat them as one object. And I want you to think now, what are the forces that are external to that system of three, okay? Hopefully you'll see, and I'm going to draw these maybe a little bit fatter here, okay? The weight of M3, right, is M3G, okay? That one is external, right? The weight of M1 is external, okay? It's a smaller arrow, right? It weighs less, okay? And then we have, and I'm not going to draw these to scale, but we have the weight of M2, and then the table, right? The table's not part of the system. So those should be equal, actually equal and opposite, right? The table is external to the system. So those are the four forces that are now external to the system. What I want you to notice is what forces no longer show up. That's right, it's the tension, right? The tensions now become forces internal to the system. And this goes back to something that you need to understand about Newton's second law, right? When we write F equals ma, okay, it's written in some textbooks like this. F-E-X-T equals ma. In other words, the only thing that can move a mass is a force external to it. So when we say mass, we can sometimes mean mass of the system, right? So when you define your system as a system of three masses, the only forces external to it are the weights, right? The weights of the two masses. The tensions disappear. So watch what I end up what I'm able to do here. When I write F equals ma, and I'm going to write it again. I'm going to write it like this, where my direction is this way. Okay. Notice how this ends up coming out. I end up writing my force is going to be M3G, right? The weight of the mass 3 minus the weight of mass M1, right? Those, and that combination is moving the whole system of masses. Now look at how much easier that problem is to solve. It's like almost trivial, right? Because the only unknown here is A. And you immediately can get to your answer without the whole three system of equations thing. Right? Very simple. This is the elegance of the system approach. Okay? Notice, by the way, that these two other external forces here, they don't enter into the motion, right? They're not in the direction of motion. So they don't end up showing up in our F equals ma. So there you have, right, without plugging any numbers in now, there you have an expression that you just get immediately, okay, and that's the elegance of the system approach. Now there is one caveat to it. If you are asked to find a force internal to the system, okay, you're going to have to revert to writing F equals ma for the individual masses. Okay, so what you're going to find is you're going to get some problems like this where they say find the acceleration of the system. Well, the acceleration of the system is based only on forces external to the system. So you can do this easy way here, right? Zoom out, what I would call zoom out, take the system approach and ignore the internal forces, right? In this case, the tensions are internal to the system. However, the caveat is if the question asks you to solve for the tension between the blocks, which you often will be asked to do as well, you're going to have to go back to an F equals ma that includes tension. Okay, so right, if I go back to this one here, right, the reason that tension shows up in this particular formula here, okay, is that tension is external to M1, right? Tension in the left rope is not external to the system of three masses, but it is external to M1. So F equals ma only works when you're solving for forces external to whatever your system is. Okay, so to wrap up, right, to go back to this system approach, okay, it's a very quick and elegant way to get the acceleration of a system of masses, but then you're going to need to go back to F equals ma for an individual mass to find any forces that are internal, which in a system of masses, the tension will be an internal force. So the way that applies to, let me go back to the first screen, the way that applies to this problem right here, right, because there's no tensions here, is there are still forces internal to the system. Okay, there's a normal force of, if I call this block A and this block B, right, would you agree, if you remember from your, you did a worksheet on this earlier, but A is pushing on B and B is pushing on A, and those are action-reaction forces, right? So those are forces internal to the system. So you can actually take a system approach here, right? You can treat that set of two blocks as one system as well, rather than writing F equals ma for each individual block or each individual box. So there you have it, an alternate approach to deal with multi-body problems. But I want you to notice at the end of the day that you're still approaching these problems exactly like every other Newton's laws problem, which is draw a sketch, make free body diagrams, componentize those forces when necessary, and then quote-unquote read your free body diagram into the F equals ma equation.